The way we have done it is a very simple way. We have two electrodes which form a nanometer-sized gap in between, and then a gate, and the entire thing is sitting in an electrolyte. And then we apply a voltage between the gate and the electrodes, and by applying a voltage, we deposit atoms from the electrolyte into the gap. In this case, it was a silver atoms were deposited. So here is a gap. We deposit the atoms, and in the end, these silver atoms form a bridge that in the gap. So once a bridge is formed, of course, there is electric conductivity between the source and the drain electrode here. And the higher the applied voltage, the more atoms are deposited, and the higher is the conductivity. Now, the conductivity does not go up as a straight line. It goes up in steps of 2e squared over h. E is electronic charge, and h is Planck's constant. And the reason why it goes up in step, because the wavelength of the charge carrier is larger than the size of these silver channels in the gap, and therefore you get these quantum effects. And the smallest increase, of course, which we can generate is 1 times 2e squared over h. So we tune the voltage that it just goes up and down by 1 times 2e squared over h. This is shown here. We had to tune the voltage between 0 and minus 25 millivolts. This is a voltage between the gate and the electrodes. So this is a voltage applied here. And so we go up and down by 25 millivolts, up and down. And here you can see the conductivity jumps up and down between 0, down here, and 1 times 2e squared over h. And you can do that many thousand times. You always get the same answer. And the conductivity of 1 times 2e squared over h is very well known. This is a conductivity of a single atom coordinated channel. So you have a pair of atoms, and all the electrons go through this one channel. This is what we get at minus 25 millivolts. When we go to 0, the channel opens up. Conductivity is 0. When we apply 25, it closes. The atoms hop forth and back, and this is why this thing jumps up. Now, obviously, if that is so, then of course you would expect if the voltage is larger, then you can make a channel of 4 atoms, 6 atoms, 8 atoms, and so on. And this is indeed true. I'll show you an example here. Here in this case, we change the voltage between 7 and minus 27 millivolts. This is the voltage. And here you see the conductivity. It jumps up and down between 0 and 22 times 2e squared over h. To 20 times e squared over h, I mean 11 times 2e squared over h. That means 11 atoms go forth and back all the time. And again, we can do that many thousand times. It always does the same thing. Now, in order to understand that a little bit better, what we have done is we have computed the atomic structure of this channel in between the two, in the gap of the two electrodes, assuming that we can, in a simple way, represent the electronic structure by a Higgs approximation, and assuming that the silver grows in a 1-1-1 direction, because that's the preferred direction of growth of silver. And the answer, what we get from the theory, is shown up here. So we have here the one electrode and here the other electrode, and the smallest contact which we get are 2 atoms which are just bridging the gap. And then the next one is 4 atoms sitting in the gap, 6 atoms, 8 atoms, and they give us 1 times, 2 times, 3 times, 4 times 2e squared over h. And this is the theoretically predicted thing, and this is exactly what we see. So what we do is, essentially, we have our electron, and by a self-organizing process, the silver forms these 1-1-1 cones, and then the last atoms form either a pair, a double pair, a triple pair, and so on, and this is what it calls. So this allows us to, by a self-assembling process, to create these contacts, which means that we can produce self-assembled single atom transistors, double atom transistors, and so on. And these we can operate them at ambient temperature. And what is attractive to it is that the energy consumption of such a transistor is about 10 to the minus 4 times the energy consumption of a solid-state transistor. However, the price what you pay is that the switching rate here is in the order of a tenth to a hundredth of a second. Of course, a solid-state transistor has much faster switching. But at least It's a transistor which forms spontaneously off and on. And again, the same answer. If you go away from the way to look at things, go away from a three-dimensional tunable material to a one-dimensional tunable material, you get a new answer. So finally, let me say a few words about what the future might look like of these materials, and I'll go back to where I started. I started with history. When you look back in history of materials and of technology in general, then what you see is that it was always in the past the understanding of the structure and the property of a particular material, of bronze, of iron, of copper, of gold, and semiconductors. All these materials, always first the observation, then the understanding, and that led to a new development of mankind, to the Bronze Age, the Iron Age, Semiconductor Age, and so on. And in all cases, what we did was to utilize the new property of the new kind of material which we have discovered, and these utilization then lead to a new part of our technology. And now with these nanoclasses, we have a similar situation. We have a new material with new structure and new properties, and so the speculation is that by understanding the structure and the properties of these nanoclasses much better, this is the very beginning what I'm talking about here, we should be able to initiate a new development in the history of mankind, a development which you could call a glass age. So that instead of using crystalline materials, we now use non-crystalline materials, but as you can see, we can make alloys, we can introduce defects, we can do exactly the same thing what we could do so far with crystals, now we can do with non-crystalline materials. But now comes the catch. At the moment, the way we produce these things is an academic way. We can produce a gram in a very expensive way. But if somebody would find a way to produce these nanoglasses in large quantities economically, then the way would be open to a whole new technology world. And there, it's not unlikely that this will happen, because if you recall what happened in the past, for example, when aluminum was discovered by Wöhler, aluminum was more expensive than gold. And that's the reason why when you go to Washington, to the Jefferson Memorial, you find an aluminum crystal in the Jefferson Memorial, and not a gold crystal. And then came Bunsen with electrolysis preparation, and the price came down to what it is today. So if somebody would, a Bunsen, come along and tell us how to produce these nanoglasses cheaper, that would be the breakthrough, and then it should open a whole new world. And I was trying to point that out, in particular to the younger students. You should learn what is in the textbook, but don't think that the textbook is 100%. It's half of the truth. And there's another half which has not yet been discovered, and it's your job to look into this other half, and it's interesting to look into it. You will be surprised how many more things are available in nature, and we are just, one could say, too stupid to see it right away, because people could have done that experiment 50 years ago. It's just this slightly different way of looking at things is enough to see things. And finally, I would like to show the names of all the people that were involved in it. The way we do the experiment is mostly by having a certain idea, then approach a group that can do certain measurements or certain things in a particular way, then cooperate with them, and you can see the people are our partners come from all over the world. And this cooperation, of course, which makes things also attractive. So this is, of course, to appreciate their contribution. Without them, we could have done essentially nothing. And finally, of course, I would like to thank you for inviting me, and thank you for spending the afternoon with me. Thank you.
I open